Hey everyone, welcome to week 5. This is the last week that we have lectures, and then we'll focus on a slightly different but very important topic, which is image and video generation, which we see a lot of examples nowadays. So we'll start the week with an overview, and we'll go over various different approaches for generating content. We'll go over VAEs, GANs, autoregressive modeling, and diffusion models. And then we'll switch to the details of building a text-to-image model. We'll go over best practices for data preparation, different architectures such as UNet and DIT. We'll review briefly forward and backward process in diffusion models, and also how sampling works, how can we really generate images once a model is trained. And then the second part of the lecture would be about text-to-video models. Basically, we'll try to extend text-to-image to text-to-video. And then we'll also learn about the best practices to build text-to-video models. We learn how it's different from text-to-image, and what are the computational challenges and how can we fix them. And finally, we have project 5, which is building a multimodal generation agent. Basically, this project is very important because now we put together a lot of things that we learned, and we built something similar to ChatGPT, well, a lot simpler and less smart. But basically, we built an agent that you can ask questions, like generic questions. You can ask it to generate images, or you can ask it to generate videos. And then this agent would identify the request and call the corresponding model to serve your request. So yeah, it's going to be an exciting week, and let's start. So first, let's see how image generation looks like in practice. There are lots of different websites and companies that are offering text-to-image generation services, and we'll go over them in detail later. But just to get an idea, this is ChatGPT, the same UI. I've not changed anything, and it's the same model. And now, instead of asking a textual question, I am now asking I have a request to generate an image. So here, this just came to my mind right before this lecture, that basically a query like, I want you to generate an image to show a diagram showing the system design of a multi-step agent, which is slightly relevant to our previous weeks. And this is a challenging prompt in general, because for these text-to-image models, they have to be really good so that they can generate meaningful diagrams. It's easier to generate images like cats, dogs, and those kind of things. But when you ask to generate a diagram explaining a certain system, it's very complex, because now logically basically everything has to make sense. You know, all the arrows, all the components, everything should be relevant. It requires a lot of text rendering. So all these are very challenging problems for image generation. So I was just curious to see how this works. And when we hit enter here, basically now you may realize that the model is not really start answering it in textual format. It identified that my request is an image generation, and it routed this request to some other models maybe, or the same model. But basically now it realized that it's an image generation task. So here it says getting started and showing this blurry image. And there are two images here. So it's basically working on it and trying to generate the image that I requested. Now it's going to take a little bit of time. It generally takes a few seconds, maybe 10, 20 seconds, or even more. And different text-to-image services may take different times. Some models are more efficient, so it takes less time. But just so we don't have to wait, I entered this exact same prompt in a different session before this video, so we don't have to wait. And then basically the model generated this image. This is an image. It's not really any text involved. It's an image with some text rendered, which is amazing. I think most of the spellings are correct. It says environment, agent, policy, value function. The arrows are meaningful. And then here it says system design of a multi-step agent. And here it says image created. So it was successfully generated an image, and the image seems meaningful, correct. All the spellings are accurate. And also it's kind of logical and meaningful. And there is also another image here. So by default, it just creates 2 images. So if one of the images are not too good or it messes up something, you can use the other image. And this image, you can see it's totally different, but still, it's basically relevant to my query. It says system design of a multi-step agent. There are some arrows. The arrows are not well. For example, this one is not really going into the environment, but I think it's still very acceptable as a model to generate an image like this. So now let's go back to our lecture and we understand how can we really build a system or a model like this to generate images. Hey, let's understand different ways that we can build image generation models. So overall, there are many different techniques that were developed over the years by the research community or by companies. And those different techniques can be categorized into 4 buckets. One bucket is VAEs or variational autoencoders. Then we have GANs or generative adversarial networks. We have autoregressive modeling and diffusion models. And as you probably know, most advanced state-of-the-art image generation or video generation models are all based on diffusions. So we would spend a lot of our time in this lecture on understanding how diffusion models work and can be built in practice. But we would also briefly review other techniques, including VAEs, GANs, and autoregressive models. So let's start with VAEs. So what is VAE? VAE is a generative modeling technique, and it was one of the earlier attempts that we were using to generate some actual images. So when it was introduced and when it was used to generate images, the community, people were very excited because it was the first time that we had a reasonable neural network model capable of generating content. And the idea was introduced in this paper, Auto-Encoding Variational Bayes, in 2013. And I also like to note that before this, there was some simpler versions of VAEs. It was introduced originally in 1980s. But then this paper made some modifications to the idea and made it probabilistic. And it was very powerful in a sense that the method was able to learn some data distribution. And since it's generative, we can sample from it, meaning that we can generate samples that are similar to the original data distribution. If you want, you can take a look at the paper, but it's very theoretical and math heavy. So there are lots of formulas. And the reason for that is that because VAEs were based on, again, it's math heavy. So it's having basically a probabilistic interpretation. And that's why you would see a lot of formulas. But the underlying idea is very simple. Basically, VAE is just a neural network and has 2 components, an encoder and a decoder. And these encoder and decoders are also neural networks, meaning that they have a sequence of layers that sequentially transform some input and generate some output. The encoder is responsible to take some data as input, let's say images. So it takes one image as input, it passes it through all those layers and sequentially transform them. And then the final output would be an encoded version of the input image. Now it can be 2D or it can be one-dimensional. These days, there are different implementations of it, but back in the days, in the original implementations, it was a 1D vector. So basically, whatever the input image is, it goes to the encoder. The encoder encodes it into a compact version, which is just a 1D vector of just numbers. So this was considered the encoded version of the image, which was compact and compressed. And the hope was that this vector should capture all the important details from the data, so that later the decoder can reconstruct this image. So what that means is that now this decoder is also a neural network. So it's a sequence of layers. And then it sequentially transforms this vector. So this vector goes input to the decoder. The layers of the decoder transform this vector through a sequence. And then the final output is supposed to have the exact same shape as the input image. And then the goal of this whole architecture is that the decoder should be able to reconstruct the original image. So basically going from this to some images that is as close as possible to the original image. And that's how VAEs were being trained. Basically, we had a training data, which was lots of images. Those images were being passed to the VAE. The VAE, the encoder, generate these intermediate encoded version, and then the decoder uses them to generate some output. And then we apply some loss. And the loss is generally the difference between this reconstructed image and the original image. For example, mean squared error is, or MSE, is one way to measure the how good the model is doing in reconstructing. Basically, we take the difference between each pixel and then square it and then sum them up. So this can be a measure of how good the reconstruction is happening. And then the optimizer is basically tries to update all the parameters of encoder and decoder so that this reconstructed image become closer to the actual image after going through this sequence of layers. So that's VAE training. And then after this model is trained, it's very good at basically, if we pass the similar images to our training data to it, it can convert it to an encoded version, and then this encoded version goes to the decoder, and then the output is going to be very similar to the input image. So now, why this is useful for image generation? Now, we can use this VAE, we can discard the encoder part of it, and then we can use only its decoder. And instead of encoding an image and then passing the encoded vector to the decoder, we can just randomly sample some vector. So here we just sample some vector from a certain distribution, let's say Gaussian distribution. And now this goes to the decoder. And then decoder generates something. And this something is basically very similar to the training data. So for example, if we train the VAE on lots of images of dogs, this is going to be most likely different variations of one of those images, like a dog, but not exactly similar to the training data. So it's going to be something new, but it's still very similar to the distribution. For example, if all the input images are dogs and it's outdoor, this generated image is very likely to be outdoor and also has a dog. So basically, this inference-wise, this decoder part allows us to generate or sample data points that are similar to the training data. So if it's images, training data is images, we are able to sample images that are new, meaning that they're not in the training data. Let's see an example to better understand the training data and distributions. One of the popular data sets that were initially used to train VAEs were MNIST dataset. And MNIST is basically just a database of handwritten digits. It has 60,000 examples for training and 10,000 examples in their test set. And it's 28 by 28. I don't know if it's mentioned here or not, but basically the images are 28 by 28 and it's black and white. So you would have 60,000 examples of just handwritten digits of size 28 by 28. So this is how the examples look like. So these are the images, and they have their different examples, different ways of writing 0 or 1 or 2, all the way to 9. And then the hope was that to learn this distribution, meaning that to train a VAE that learn from this, and then we can sample from it, meaning that we can generate a new image similar to this that look like handwritten, but it's not also in the original training data. So this is an interesting implementation. I don't want to go exactly go over all the details of it. I just want to get an overview and high-level understanding that VAEs are very easy to implement. So later, if you are interested, you can just go to this website and go through every detail of the code or even implement it. But my hope is just to go over very quickly the implementation of VAEs. So again, VAE is just a Python class, and then it inherits from NN module in PyTorch. And this is very standard. Basically, there is init, and then we have this forward function. And that's how it's expected to write new PyTorch models. But basically, if you look at the initialization here, it has an encoder and it has a decoder. And basically, the encoder is just a sequence of layers. And it has basically two linear layers with some nonlinearity in between to make this overall sequence of layers nonlinear. So you can see the input dimension is the size of the input images. And then there is some hidden dimension, meaning that it transforms the input dimension to some hidden dimension, which is smaller. So in our case, input dim is 784. And this is because MNIST is 28 by 28. So if you multiply 28 by 28, we would have this 784. Now, it goes from 784 to 400, hidden dimension. And then another linear layer also goes from this hidden dimension to this latent dimension, which is 200. Now, we have also this decoder. Again, I'm not going to go through every single detail, just want to get a sense of how VAEs can be implemented. So we have this decoder, which is kind of the inverse of that. Basically, it has, again, a sequence of linear layers. And now it's the opposite. Basically, it's going from smaller dimensions to bigger dimension. And the final final layer, the last linear layer, is going from hidden dimension to the input dimension. So the final output is going to have the exact same shape as the input dimension. So this is the architecture. This is how it's implemented. And this part is basically, it has some probabilistic interpretation. Basically, instead of this model to output a single vector, it's outputting two vectors. One is a mean and one is variance. So at inference, we can just sample from those mean and variance. Basically, it's just outputting a distribution. It's not outputting, in practice, it's not outputting a single vector. It's outputting a distribution. So two vectors, one mean and one variance. So we can sample from that. And this is why we have this code here. So it goes to from latent dimension to 2. So basically, in this implementation, this is of size 2. So basically, every image is being mapped into a point in two-dimensional space. And then same for the variance. So this is mean, this is log of variance. And then if you look at the actual encode function, so when the X goes into this encode, it passes it through the encoder. So this is going to be of size latent dimension. And then it passes this X into the mean layer and logvar layer to get those vectors so that it can sample from. So this is mean and this is logvar, and then the dimension is 2. And then decode is basically just passes the input to the decoder. So now the forward function is very simple. First, whatever the X is, it's passed to the encode, and we get this mean and logvar. Then we sample from it, meaning that we randomly sample a point from this distribution. So if you look at this function, it's just randomly sampling a point. It has mean plus var multiply eps, and this epsilon is basically randomly sampled. So basically, so the forward, it encodes, then it samples from this compressed distribution that was outputted by the encoder, and then it decodes it. And this is the reconstruction of the input image. And then this X hat now is going to be compared with the original X, and then the loss function would be applied and optimized. So here is the loss function. Here it's using a simple binary cross-entropy loss. And again, you can have different loss functions for VAEs. And this is a pretty standard training loop. It's in most PyTorch codes for training neural networks. This is basically very standard. We have a loop over all the epochs, basically number of times that we want to go over every single example in the data set. And then we go over the data loader, meaning that each time we load a batch of images. This part is basically changing the dimension from 2D to 1D, because again, images are 28 by 28, but our architecture, the encoder, its first layer expects a one single input dimension of size 278. So we need to just reshape or change the view of the images. So this is what is happening here. And then the rest is just setting the optimizer, getting these values, applying loss, and then backward and optimizer.step to update all the parameters. So after this is done, now we can sample from it, meaning that we can randomly pick some mean and log var. Here we set them to a fixed values, but it can be randomly generated. And then from here, we just create this sample, decode it, and get this X decoded, which is a new image, but it should be very similar to the training data. So in this case, you can see it's something like this, which is 2. And again, it's very unlikely that there is an image in our training data which is exactly like this. So it's a new image. So that's it. And then this part basically is just visualizing different values of mean and variance. So you get a sense of how with different values of mean and variance, what would be the output that is generated by this VAE. So again, this part is what I just mentioned, that basically the output is has 2 values so that it becomes a distribution. So we sample from this distribution for generation. And then this is also a nice visualization. After training a VAE, if you inspect its learned latent space or the learned distribution, you would see something like this. Basically, all these points are some training examples that are mapped to this 2D after it's passed to after it's encoded. So, for example, you can see this is 5 probably, and you would see that there are also different clusters. So the VAE, the encoder part of the VAE, is mapping, for example, all ones to this area, and also mapping all 3 to this area. So you can see it's basically trying to separate them out in this 2D space so that it has an easier job to reconstruct them. And then any point, if you sample from this space, for example, if you come here, you would see it's 0, and here is empty, so it's white, meaning that there is no training example here. So if you randomly sample a value of, you would see the mean and sigma here. So as I move here, for example, here the mean is 0.902 and sigma is 0.002. And there is no image in the training data with these values after being encoded. So it's going to be a new image. And here on the right, you can see the actual image if you sample from here. And you can see if you are somewhere in between, this can be a little bit confusing, like between 8, 6, 5. And then if you're here, it's very off if you are too far from the center of this space. But anyway, this is VAEs, and you see how an encoder can learn a latent space, and then this latent space can be used to sample new data points from it. All right. One more thing I want to say about VAE is that it's really no longer used for image generation these days or any kind of generation because they're not good enough. A lot of times when you sample a data point from that distribution, the samples they're blurry. So that's one main issue. So it's very hard to have really good images with fine details. But still, VAEs are very powerful and they are used for other purposes. Even in diffusion models for image or video generation, we still use VAEs, but for a different purpose. So once we start talking about diffusion models, then we would see where this VAE is being used. So I just wanted to point out that it's not really used for actual generation, but still it's used for other purposes in diffusion models. Now let's go to the next technique, which is GANs, Generative Adversarial Networks. This is another generative modeling technique, and it was very revolutionary by the time it was introduced, because again, back then, the best tool that we had were VAEs. So the images that we were able to generate were usually very small and blurry and not high quality. And GANs were suddenly able to change that. And the idea was first introduced by Jan Goodflow. And when I was at Google, he was there. So one day there was this talk that he had, and he was explaining about how he came up with the idea and the process. And it was very interesting because he was an intern at Google when the idea came to his mind. And then on some evenings, he invented the idea, he implemented, and he got really amazing results the next day. And then very quickly, I think he published a paper, and then the paper became super popular. So this is the paper, Generative Adversarial Networks. And I think it's cited hundreds of thousands of times, if I'm not mistaken. But it quickly became one of the most popular papers in the computer vision and neural network history. So you can read the paper. Again, there are lots of details, but it's a lot simpler than VAE in terms of mathematics. And it's relying more on a game theory. So let's go back to our lecture. Basically, now the idea is that we have two components to build a GAN. One component is a generator, and another component is a discriminator. And again, these are just neural networks. So each of these, they are just having a sequence of layers, depending on what their purpose is. Now, the generator, as the name indicates, is responsible to generate an image. So it starts from some random vector, which we randomly sample. The generator, through its sequence of layers, transforms this random vector into some generated image. And then there is this discriminator component, which is also a neural network. Now, this component is responsible to discriminate whether a given input is fake or it's real. And by fake, we mean it's AI generated. It's basically generated by this generator, or it's a real image coming from some data sets. So this generator piece generates something. This discriminator piece is just a classifier. So when the GAN is being trained, these two play against each other. The generator tries to generate better and better images. The discriminator becomes better and better at distinguishing between fake and real images. And basically, there are some loss functions that are applied both for this generator and discriminator. The loss function for generator is, in simple terms, it's basically to generate images that cause discriminator to confuse or fail. So basically, the more the discriminator make mistakes, the higher the reward would be for this generator, meaning that the loss would be lower. So if the generator can generate images that this discriminator cannot discriminate, then it would have a low loss. Otherwise, the loss would be high. And then for discriminator, it's a classification problem. So the loss is very simple. It's just a cross-entropy loss. And if the discriminator does a good job at classifying fake images as fake and real images as real, it's going to have a low loss and otherwise a high loss. And then the optimizer tries to update the parameters of discriminator and generator simultaneously and iteratively to make both of these components better. Now, there are lots of challenges in training GANs, and there are lots of issues that can be tackled in different ways. You can read the paper. There are lots of great tutorials and courses out there if you are interested to learn more about those. One example is this Google's course for overview of GANs. So they talk about how GANs are, what is the architecture, how they are trained, and discriminator piece, generator piece, training, and also common problems here. So if you're interested to learn about the actual challenges in training, like mode collapse, and vanishing gradients. These are some of the common issues when we are training GANs, and how to address those and remedy. So if you're interested, you can take a look. Our purpose is not to go too deep into these techniques because they're no longer used in advanced text-to-image, text-to-video models. So we just want to have a brief understanding of the technique. But again, this is how GANs are trained. Once you train a GAN, you have two components with optimal weights, generator and discriminator. Now at inference time, we can discard discriminator. We no longer care about whether images are fake or real. And we only keep the generator. And then we can randomly sample from the same normal distribution that we were sampling during training. And now this time, the generator should be able to generate images that look like real or look like it's training data. So this is high levels of GAN, how they are trained and how they work to generate images. And again, they became very popular, and very soon there were lots of variants to improve GANs. This is Wikipedia. If you see, there are lots of different variants here. We have conditional GANs. There are GANs with alternative architectures, DC GAN, SA GAN, VAE GAN, Trans GAN, Flow GAN. And then there are different objectives. There are also like different ways of setting this game and conditioned like bidirectional GAN. So cycle GAN was also very popular at some time. But again, there were all these different variants of GANs were just incremental improvements over the original paper. And then the results they were getting were really, it was getting really better and better. And then at some point, NVIDIA had this paper called the Style GAN, and then the Style GAN family. Later, they introduced the Style GAN 2 and I think 3. And you can see how images were looking a lot better and more real compared to like those handwritten digits that we saw for coming from VAEs. So that's why everybody was very excited about GANs, and companies were trying to build on top of it and improve it. So yeah, if you're interested, you can also read the Style GAN paper. They made minor modifications into the architecture so that also a key, one thing interesting about the Style GAN was that it was allowing to manipulate the facial attributes. For example, you could make this person to smile or look happier or cry or with sunglasses, without sunglasses, and all those changes. And the reason for that was after training the GAN, it turns out that the learned data distribution is very smooth, meaning that if we just walk over it, there would be no jumps in the generated images. There would be a smooth transition. So at some point, some papers realized that there are some dimensions that if you walk over them, it would change the attributes, certain attributes. For example, it would change how happy or if somebody is smiling versus not smiling. So these are details. We are not intending to go into them. If you are interested, you can read the Style GAN papers. But that's GAN. Now let's go to the third generative modeling technique for image generation. So the third class of generative modeling of images and videos is autoregressive modeling. And basically the idea of autoregressive modeling is to formulate this task of generation differently. Instead of having two components playing against each other, like generator, discriminator in GANs, or in VAEs where we had encoder-decoder to go from the original image to a smaller, lower dimensional latent space, and then from there we reconstruct the images. Here we model the task, we formulate it as a sequence generation task. Because the images, basically each image, we can think of it as a sequence of pixels or a sequence of patches, where each patch can be a set of pixels, like 3 by 3 patches. But regardless of how we break the image into smaller pieces, whether it's patches or pixels, let's say pixels, we can generate it sequentially, one by one. And that's the main idea behind autoregressive modeling. Basically, we train a model to learn the conditional distribution of these pixels or these tokens. So for example, let's say for training, we have a real image here. We can, let's say, we just convert it to a sequence, 1, 2, 3, 4, and each of these can be 1 pixel of this real image. And then we train a model on this sequence to learn the distribution from this sequence and all the co-occurrences of different pixels. And then once it learns it, it can predict them sequentially, one by one. So after we train this model on lots of different images on our training data, it would learn how different tokens or how different pixels follow each other, how they relate to each other, and what is their distribution, how they co-occur. So at inference time, all we need to do is we need to just start from some random initial pixel, pass it to the model, and then the model would sequentially generate pixels one by one. And each time, each pixel is conditioned on all the previously generated pixels. So for example, here, when it wants to generate the third pixel, we are conditioning this model on all the previous pixels. So this idea was first in this paper, conditional image generation with pixel CNN decoders. And I think it was by Google Brain. It's coming from DeepMind in 2016. So they introduced this idea of formulating the image generation as a sequence generation task. And here you can see they're using some convolutional neural networks to go over an image and learn the locality and how different pixels are appearing together. And then it tries to, at each step, it tries to predict this pixel given all its neighboring pixels that were generated. So it's a conditional generation. And the model that they're using is based on convolutional neural networks, or CNNs. So there is no transformer in this work. But then later, there was this paper called Image Transformer, and I think this was also published by Google Brain Team. Yes, by Google Brain Team in 2018. And the idea is very similar to Pixel CNN. Now, the main difference is that instead of using a CNN as the backbone of the model, they're using a transformer because they realize that transformers can be more capable and they are very good and designed for learning from sequences. The transformer, remember from previous weeks, were initially designed for language modeling. So it's really good when we are dealing with a sequence of tokens. The transformer can use as a self-attention mechanism to attend to all the previous tokens and learn from them, and then predict the next token with high accuracy. And since in autoregressive modeling of images, we are converting this into a sequence of pixels or numbers, transformer is naturally a great fit for that. It can use as its self-attention mechanism to attend to all the previously generated pixels. And then based on that, it can generate the next pixel. So I would say there is not a lot of novelty in this paper. It's mostly replacing the CNN with a transformer, of course, with some details and minor differences. But the high-level idea is just to use a self-attention mechanism and transformer to generate images pixel by pixel or block by block. So this is autoregressive modeling. The next thing I want to talk about is that autoregressive modeling, and in particular this setup, has another great advantage over VAEs or GANs. And that advantage is because of the flexibility that transformers give us. So again, remember, this model, we can replace it with a transformer because they're good at processing these sequences. Now, the advantage that we are having when we are using a transformer is that we can easily condition this generation process on something. For example, we can condition it on some classes. So we specify what category of images we want. For example, we can say dog, or we can say cat, or we can say desk. And then the transformer can, at some layers in between the model, called cross-attention layer, it can condition on the provided input text. So during this generation process, it's not really going to randomly generate these pixels to form some random image in some random category. It would generate these pixels given the text, the category that we are providing it as a condition. So what that means is that we can easily also extend it to text-to-image generation. Instead of providing a category, which is dog, we can have a textual description of what we want. And then the transformer would be able to handle it, because whatever our text is, we can tokenize it, and it's going to be, at the end of the day, it's going to be a sequence of numbers. And then the transformer architecture, at some point, we can have a self-attention mechanism and cross-attention mechanism. So when it's trying to predict the next pixel, it attends to the provided input text, which is also a sequence of numbers. And this idea was first, I don't know if it was the first, but it was the first successful attempt of using transformer for text-to-image generation. It was a work named DALL-E by OpenAI. And it was published in January 5th, 2021. And they're using exactly the same idea. They are formulating the task of generating images as a sequence generation task. And then under the hood, they are using a transformer. And then the transformer is predicting the tokens one by one, the image tokens one by one, conditioned on the text input. And this was the first very successful attempt to generate images conditioned on text. For example, here they have some examples: an armchair in the shape of an avocado. And these are some of the AI-generated images. You can see how capable the model is to generate novel images conditioned on this provided text prompt. And if you are interested, this is their paper. It's called Zero-Shot Text-to-Image Generation. And the underlying idea is, again, they use a transformer and they condition on text input to generate images. So that's all about autoregressive modeling. So their main advantage and strength is that they can be trained using transformer model. And because of the self-attention, these models are very good to generate high quality, high resolution images that are coherent, meaning that all the pixels are meaningful and relevant if you look at the image globally. And they're also very flexible in a sense that we can condition it on different types of inputs, such as textual description. But still, with all of these, autoregressive modeling is not the best technique for image generation. Most advanced text-to-image, text-to-video models these days that you would see are, almost all of them, to the best of my knowledge, are not based on autoregressive modeling, but they are based on diffusion models, which we would talk about next. So what is diffusion models? Diffusion model is also another class of generative modeling, but what they're doing is they are formulating this image generation task differently. They're not formulating it as a sequence generation task to generate pixels or patches sequentially, but instead it's an iterative process. And the idea is that given an image, we add noise to it, and then we train a model to iteratively denoise it. So here you can see this is in our training data, let's say, the original images. So we add noise to this through a sequence of steps. And then at some point we have a noisy image of the original image. So you would still see some visual cues of the original image in this noisy image, but it's not as clear as the original image. And then at this point, we train this diffusion model to predict the noise or predict a slightly denoised version of the image. So for instance, once we pass this, the model may output something like this, which is still a lot noisy, but less noisy than its input. So if we have this model, now we can iteratively use it to keep denoising the image step by step until we get an image which is clear and high quality without any noise. And then this is going to be during the training time. We are enforcing it to be the reconstructed image because we've started from this. We basically update the parameters of this diffusion model such that it becomes very good at predicting this. And this is going to be as close as the original image. And then at inference time, it's also very simple. Once we have this diffusion model, now to start this image generation process, we can start from some random noise. We can randomly sample a noise, and then we can just pass it to the diffusion model. And then the diffusion model would denoise it step by step. And at some point, it would generate a new novel image that is an approximate of the original training data distribution, but it's going to be an unseen and new image. So since diffusion models are very popular and are powering most state-of-the-art text-to-image, text-to-video models, we are going to focus more on diffusion models, how they are built, how they are trained, and how they are used in practice. in the rest of this lecture. But before that, just to show some papers in case you are interested. Diffusion models were first introduced in this paper in 2015. And here, basically, it's very math heavy and theoretical of, what is diffusion process, what is forward process, backward process, and how to learn a data distribution, and so on. But then later, this paper in 2020 from UC Berkeley came out. Its title is Denoising Diffusion Probabilistic Models. And this was the first time that a paper were able to use diffusion models to successfully generate high resolution images. So here you can see some sampled images from a certain data set that it was trained on. And these images are 256 by 256, which was, again, impressive back then for the first time generating these images that are high quality, they look real. It was very surprising and very exciting for the community. So this is an interesting paper. If you are interested, it describes how diffusion process works, how they train this model. But we are going to learn the high levels of diffusion process and training in a bit in our lecture. So if you're interested to learn the details, you can go through this paper. But one last thing before we go into the diffusion models is that how amazing it was to go from a quality like this from MNIST to generate images like this of 28 by 28 to images like this using diffusion models in just a couple of years. And just so I show you something, there was this DALL-E 2. We saw DALL-E 1, but there was this DALL-E 2 paper published by OpenAI shortly after this paper. So this is DALL-E 2. And then we saw DALL-E 1. DALL-E 1 was text-to-image model based on transformers and using autoregressive modeling. DALL-E 2, due to the success of diffusion models, they changed their approach of switching from autoregressive modeling to diffusion modeling. And it was also text-to-text conditional, meaning that you can provide text, and then the diffusion model conditioned on the text would generate some images. And you can see here the images were quite impressive compared to the state of the art. And you can see here, for example, images like, you can see these examples. Most of them look quite impressive, like a teddy bear on a skateboard in Times Square. And everything looks natural, high quality. And this is very impressive, this to get here from MNIST here within just a couple of years. And this is now relatively old. If it's a couple of years ago, we'll go over more advanced state-of-the-art models. And these days, these image generation models are capable of generating very high quality, high resolution images a lot faster and a lot cheaper. So we will learn about most of those state-of-the-art models in our lecture. So that's it. Hello, everyone. We'll continue our discussion on generative modeling, and we'll see what is the landscape of image generation and how can we really use diffusion models and build them and train them. In the last lecture, we went over key generative modeling techniques. We went over VAEs, GANs, autoregressive modeling, and diffusion modeling. We also saw that VAEs and GANs are like earlier methods. They are not, the quality of their generated images are not as good as today's standards. And then autoregressive and diffusion models are both showing a lot of promise, and they are very capable at generating high quality, high resolution images. So here's a summary of different approaches, and you can take a look offline. But basically, the first two rows are important, quality and speed. And as you can see, VAE and GAN are lower in quality, and they are no longer acceptable for today's need or demand. Still, GANs are better than VAEs, but not too good. And then both autoregressive and diffusion models are very impressive in terms of quality of generated images. A lot of companies and startups and also papers observe that diffusion modeling works better than autoregressive modeling. It leads to higher quality, like visually more aesthetically nicer images. But still, occasionally you may see papers or some companies trying to use hybrid approaches or building something based on autoregressive modeling. But most of the models and advanced text-to-image generation models that we would discuss and we would see are all based on diffusion modeling. And in terms of speed, it's the opposite. So VAs and GANs are very fast, whereas autoregressive and diffusion models are generally very slow. So there are a lot of challenges and therefore opportunities to optimize and make generation faster in those images, in those techniques. So it's an active research area, and a lot of different techniques are proposed over the years to just make the generation faster. So the next thing I want to talk about is image generation versus text-to-image generation. So far, we saw that those generative modeling techniques are capable to generate images after training. But these images are often random, meaning that you have no control over this output image. You basically, the model, whether it's diffusion model or VAs or GANs, generally start from a random noise. And then it goes through those layers, and then it's transformed into a clear image. And this clear image, it can be anything, and it's going to be an approximate of the training data that we use to train this model. Now, this is not desirable because as user, we don't have control over the image that we want to be created. For example, there was this website, just to get an idea, this person does not exist, and it's quite old now. It was built in the generative adversarial network era, and I think it's powered by a GAN. So basically, the idea is each time you load this URL or refresh it, it would use the trained GAN and generate a sample from it. So it generates one image and shows it here. So these are not real people. These are the ones that were generated by GAN. And if I refresh this page again, we would see another person. And again, this shows that what I mean by random generation. Basically, I have no control over specifying what I want to get, whether I want to get specifying the gender, specifying the attributes, like if I want somebody to wear glasses or not wearing glasses. So these are some of the things that many users may want, but these models are not really giving me that opportunity to control the output. Again, there are some variations of GANs in particular which gave this opportunity, but ideally we want models to, so we can specify in text format that, hey, this is what we want, and the model can just generate it. So because of that, the industry and papers and the startups moved toward text-to-image generation models, or T2I models. And those models are just an extension of the same technique, like whatever, let's say if you are autoregressive modeling or diffusion modeling, it's just being extended so that now it is a conditioned generation, meaning that a user can provide a text as the condition, and then the model would start generating the output, the image, conditioned on this text. So this way, we would end up having control over generation, and it's a lot more useful for people. So a lot of the papers and models that you would see are mostly text-to-image generation, not pure image generation. And because of that, we would also focus on building text-to-image generation, and we'll see what is the landscape there. So after the diffusion modeling success, more and more companies started building and training their own text-to-image models and releasing it to the public. For example, OpenAI had DALL-E family. So DALL-E 1 was built in 21 and released in 21. And we saw that DALL-E 1 was autoregressive based. And the output resolution of it was 256 by 256. The year after, they built and released DALL-E 2 in 22. And then DALL-E 2 was mostly very similar to DALL-E 1. The main difference was that they were switching from autoregressive modeling to diffusion modeling. And they were seeing a huge quality gain. The other advantage was that this DALL-E 2 was able to generate images of not only 256, but also at higher resolution, like 512 and 1K. And they also have this release page here, and they're showing some examples. And if you see, for instance, here is a photorealistic image of an astronaut riding a horse. And as you can see, the images are impressively good. They are aligning well with the input text, and they look correct and high quality. So it was a huge success back then, DALL-E 2. And the other good thing about DALL-E 2 was that they released a paper with technical details. So here, it's the paper. If you're interested to go over it, it's a very nice read. And they're having these examples here, which are impressive. They are very accurate. For example, a teddy bear on a skateboard in Times Square. We can see the image is semantically meaningful. It aligns well with the text. There is a teddy bear. There are people, and it has textures. So it's working quite nice. And these images are 1K, so it's high resolution. And again, the interesting thing about this DALL-E 2 paper is that it's the architecture is known, and we know how it's built and trained. And this is the architecture. We are in our lecture, we would go over building diffusion models, and we would learn how they work. So there is a good overlap between what we would discuss and DALL-E 2. But if you are very interested to learn specifically about DALL-E 2 architecture, because they have some additional components like priors, and they have some techniques that they're using, so feel free to read the paper. But we are going to cover diffusion modeling in our lecture. So that's DALL-E 2. And then a year after, again, they released another text-to-image model, DALL-E 3. And then this was even better. So basically, every time they've released a model, it became a lot better than the previous models, or sometimes more capable in terms of having more features or being able to generate higher resolution images. For example, DALL-E 3 was able to generate 1K and also different aspect ratios like a square, landscape, and portrait. They also have a page for it here, but unfortunately, there is not a lot of technical details. They have just some examples and some improvements. So I believe it's still diffusion-based, but basically, this is the page. It lacks technical details, but it has some nice examples. And then in 2025, recently, they introduced GPT-4o. And then in June, they introduced GPT Image 1. And again, there is not a lot of technical details available, but these models are very impressive, especially in text rendering. So we saw that these older models are generally struggling with rendering text in the generated image. A lot of times they misspell or the text is not accurate. But these models are quite impressive in text rendering. They have also this page here introducing 4o image generation. This was March. But again, in June, they have now this image GPT-1 or GPT Image 1. The namings are always confusing with OpenAI, but it's basically GPT Image 1, which is their latest model, and it's the best model out there. So again, we don't know much about the technical details of GPT-4o and GPT Image 1 models from OpenAI. We just have these examples, and they're doing impressively good. For example, here you can see almost the text. There is no misspelling. Everything is correct. Model compressed representations, and then the text is also meaningful, meaning that if you read it, it's following a certain topic, which is very nice. And you can see more examples, basically. So, and also more features like improved capabilities like text rendering and multi-turn generation and so on. So there is formally, we don't know how it's built, but there was this paper, GPT Image Eval, and then it's going over some evaluations and a little bit of reverse engineering and guessing how GPT Image 1 or Image, what was the name? GPT-4 image and GPT Image 1 might have been built. So you can look at this paper. Again, it's a speculation, but still it's nice material, and a lot of the content that they're sharing makes sense. And the idea, basically, the TLDR is that they believe there might be some hybrid architecture of both diffusion modeling and autoregressive modeling. So autoregressive modeling is basically making the model capable of text rendering. And then there is this decoder, diffusion encoder, which helps with the decoding and generating very high quality images. So a speculation, but it's a nice read. If you are interested, you can take a look. So that's about OpenAI's family of text-to-image models. And one last thing before switching to Google, a real example. So I went to ChatGPT and I entered something like a taco studying machine learning at sunrise on a mountain, on a mountaintop. And basically the model is using their best image generation model, which is GPT Image 1. And then this is the result that I got. It's very reasonable and it has taco, it aligns well with my text. And it could have been better. For example, the laptop has a different direction. Ideally, it should have been basically the taco should have been looking at the laptop and so on. But again, it's very, very impressive. So, and there are two examples. All right. Now let's go to Google. Google also started to build its own text-to-image models. The first one was started, they named it Imagen 1, and it was in 22. And again, it's a very similar story, very similar pattern. Each time they released something new, it was impressively better than the previous versions, both in terms of quality and capability also, meaning that the model were generating higher resolutions, different aspect ratios, and so on. So they had Imagen 1, and then it was only doing 64 by 64. And then Imagen 2 next year, 1K, Imagen 3, 1K, different aspect ratios. And then the latest model is Imagen 4, which they released two models, Imagen 4 and Imagen 4 Ultra, I believe. Imagen 4, yes, and Imagen 4 Ultra. So you can take a look. Again, it's as impressive as the OpenAI's model. It's doing excellent in text rendering. It has a very high text alignment, prompt alignment. And you can see there is no misspelling. All the text is correct and it looks very nice. And also it's capable of generating images in different styles or different domains, which is very nice. And these are generated using Imagen Ultra 4. And this looks quite real, but it's generated. So, and here, I think they're sharing the exact resolutions that this model is capable of generating. And also it accepts prompts in different languages. So no matter which language you use, like Korean, Japanese, English, Spanish, it would still able to understand your prompt and generate the output in various aspect ratios. So that's about Google. And what I wanted to do was I also wanted to compare a couple of different best models out there using the exact same prompt. So I went to Gemini and then I asked it to use, basically it uses its image generation models. And I used the exact same prompt that I used for OpenAI to see how it's compared. So here you can see I entered generate an image of a taco studying machine learning at sunrise on a mountain top, same prompt. And here the model is doing a little bit of thinking and reasoning. For example, you see here it's analyzing and it decides to use a certain tool called image generation. Now this goes back to our previous weeks, which we learned about tool calling and reasoning. So the model reasons and then believes that it has to call image generation tool. And it passes the prompt to the tool or maybe an improved version of this prompt. But regardless, this is the image that they generated. And it looks, to me, it looks better compared to the ChatGPT one. Basically, when I zoomed in, I saw it's machine learning is spelled in this book, and then there is this laptop, and then in the laptop it has some like diagrams. So it makes a lot of sense. And then the taco is looking at the book, which is also nice. And the physics also seems correct. I mean, for example, the laptop is placed here, and then there are books on top, and so everything looks quite natural and impressive. So this is about Google, and these are basically the best advanced text-to-image generation technologies out there. One more thing I want to say is that there is not only OpenAI and Google, there are a lot of other companies that are trying to build their own version of text-to-image models with different capabilities for different use cases. Some of the notable ones are Flux, Midjourney, Stable Diffusion, and this list is not comprehensive. There are a lot of different models and companies that are out there. But Flux recently is doing very good and impressive. So I also wanted to check that. And this is the UI. If you go to Flux website, it's BFL, Black Forest, let me check, Black Forest Labs. So this is the company behind Flux. And then you can choose the model and so on. I just created an account right before this lecture, and it gives like 200 free credits in case you are interested to just explore it and play around. But basically, it gives 4 options for image generation. One is generate, one is edit. So you can upload your image and then you ask it to edit. Fill, so for inpainting, and then expand to like outpaint it. So I'll use the generate, and here you can enter anything and run it. So I did that. Use the same prompt again. And then these are some of the examples that I received. Again, most of them are nice. And I also like these more than the OpenAI for this particular example, because the taco is looking at the content or at the iPad or whatever that it's holding. So it looks just better to me, but it might be this example only. So you can say this is one. By the way, the taco itself to me is not as real as the Google's taco, but maybe that's just a personal opinion. All right. And then, so going back to the lecture, one more thing is it's very impressive how we went from MNIST using VAEs to generate handwritten digits in 2015. And within 10 years, we were able to go from this to something like this. And then, again, we have a leaderboard similar to LLMs for text-to-image models. If you go here, you would see the current ranking of text-to-image models. Right now, the highest rank is GPT Image 1 from OpenAI. And then right after that is Imagen 4 Generate, and it's by Google. And they are very close, I think, in terms of the score. And then right after these two very well-known big companies is Flux by Black Forest Lab. So that's why I mentioned that it's doing quite impressive these days. And then these two models are ranked tie. They are having a tie with also this model, Seedream from ByteDance. And basically, you can see more and more models, like Imagen 3 is the older version of Google. And then at some point, you may see Dolly's as well. So here is Dolly 3. So it's a long list. And another interesting thing to note is that the license. So most of these models are closed. They're not publicly available to use or build on top of them. And then the first open model is Flux, which is also nice. And then after that is a Stable Diffusion open model. But there might be a huge gap between the quality of this model and the best image generation model out there. And again, if you're interested, there are some websites that give you access to different models and comparing different capabilities. One is fall.ai. And again, if you're interested, here is basically a bunch of different image generation models, like this is Qwen image, and you would see a bunch of other image and video models. Here are also video models, VO3 and so on. We would cover videos shortly. So if you're interested, you can go there and just play around with all these different models. So back to our lecture. I covered everything about the landscape of text-to-image models, how they work, how they are compared. Now, next, we are going to focus on the technical details of building, how to build, like technically how to build a diffusion model and train it and then sample from it. Okay, how to build a text-to-image model. And we are interested in diffusion modeling. So the focus would be on diffusion-based text-to-image models. Similar to all other machine learning models, when we want to build them, it has 4 aspects or 4 steps. The first step is to figuring out the data. What data we are going to use, how should we prepare it, and use it for training. The second aspect to figure out is the architecture. Depending on the need and what we want to train, we have to figure out how to build this model. What are the right sequence of layers to put together? The third aspect is the training part. How are we going to train a model? What is the input, output? How do we define the loss function and what is being optimized? And then finally is the sampling, which in this case is diffusion sampling. Basically, after the model is trained, how are we going to sample new data from it, generate new images? So these are all 4 aspects that we would cover. And we would, along the way, we would introduce more papers if you are interested to learn in detail or more technical or theories. So let's start with data preparation. Remember, this text-to-image system, it's expected, or our ideal system is it accepts a text prompt like a boat on an ocean, and then it generates image. And machine learning models are going to learn from training data. So what that means is that our training data should be in a similar format, meaning that we should have a training data of pairs, and each pair has an image and also its corresponding textual description, or we can call it caption. And we need to have millions of those pairs in order to train a diffusion model successfully. Now, there are different pre-processing because on internet we can collect lots of different images, and many of those images are coming with some titles or captions which are specified by users. So we can collect all of them, but all of them are not necessarily useful for training. Many of them are noisy. They may not be in a format or a structure that we want for training. So it requires some preparation, both the text part, which is like caption part, and also the image part. And each of them have separate techniques. For example, common techniques for text preparation is, so there can be a couple of issues with the text. One is that we might have some rows in our training data which has an image, but the caption is missing. So we need to handle those missing captions. Also, this data might be noisy. So a lot of times the caption is not accurately describing the image. It may be very short or very vague, or it might be even incorrect. So we also need to figure out a way to enhance captions, meaning that to make them more detailed and more accurate. And finally, another important step in text preparation is to remove the poorly matched pairs, meaning that even after doing all of these, we might end up with an image and a corresponding caption, which still is not a good match, meaning that the prompt is not accurately describing the image. So in order to only keep high quality pairs of text images for our model, we have to just get rid of them. So how are we going to do this in practice? For handling missing captions, there are 2 ways. One is we discard those images as well, so we are not going to even train on those images. That's one option, but that's not ideal because we are going to lose those images. Those images can be very important for the model to learn from. So it's not ideal to just discard all the images which do not come with a text. The other way that in practice we can handle these missing captions is we use some pre-trained models which are really good at understanding images and generating a textual description. There are lots of different models which are trained and built for this exact purpose. So the input that they take is an image, and then their output is a very detailed textual description of the image. And in early days, there were like earlier architectures, and then over time, there were more and more and more models. And these days, even most LLMs, multimodal LLMs, can also do this. For example, if you go to ChatGPT and upload this image and ask from ChatGPT to just caption it, it would come up with a very accurate caption. And there are also other open source models like Qwen, for instance, has a model for captioning. So all those different models can be used to generate caption for images with missing captions. And that's the ideal way, because this way we are not going to lose data, training data. Also, for enhancing captions, we can do something very similar. For all the images that we have, we can pass them to some vision language model or some pre-trained models that are really good at generating captions. And we use those models to generate caption for all the images in our training data. And then this way, it's very likely that we would end up with enhanced captions, and we would get rid of all those noisy captions. And finally, after doing all of this, we can use some Vision language models like CLIP, which has two encoders, one for text, one for image, to compare. So let's say we have now a bunch of rows, pairs of text and image. We can use a model like CLIP to see what is the alignment, how well the text is really describing the image. And this is done using CLIP models. If we talked about CLIP models and encoders in previous weeks. And that's how we can just figure out and identify which pairs are still poorly matched and just remove them. So this is for text. Now, for images, we also need to have a different set of important steps or pre-processing steps. Many of the images might be small because they're collected from internet most of the times. And we don't want to use really small images in our training data, because then those small images are probably not meaningful. They might not be providing a lot of signal to the model to learn from. So those are not generally good examples. So it's common to just filter small images. Another important filtering step is deduplication, or filtering duplicated images. And this can be done by using some pre-trained models which are good at embedding images. So we can embed all these different images, run some clustering, and get rid of all the duplicated content. And in each cluster, we can just pick or sample only some of them. Or extreme cases, we sample one example from each cluster. So this way, we would identify duplicated images and just remove them or deduplicate our training data. Another very important step is to filter inappropriate images. A lot of the images might contain content which is not appropriate or desirable. For example, harmful content, content with violence, nudity, and there are other categories also that a lot of times we want to filter, and we believe they are not appropriate. So that's another important step. Then we have basically more filters. For instance, here we have low aesthetic images. We can use some pre-trained models to identify which images are low aesthetic, meaning that they're not visually nice, and we remove them. And finally, we need to adjust their dimensions. And remember, we have no control over the images. So the images that we're collecting from internet, they may come in different sizes. And most machine learning models expect a fixed size input. So that's another step that we have to do. We have to just adjust the dimensions. For example, if this is the original image, let me zoom in a bit. If this is the original image, we can resize it to make it following a fixed size or aspect ratio. Then we can center crop it so that the images become a square, because we have, again, no control over the aspect ratios. And then finally, once we have the square image, we can normalize pixels so that it improves the training stability. So these are the common steps to go from the original images to a prepared image. So that's mostly about data preparation. Now, there are a lot of different open data sets which are going through all these steps and just making the final data set available. And some are just skipping these preparations, but only providing the raw text image pairs. One popular example is Lion. This is the website, lion.ai, and they keep releasing different data sets for different purposes. And in 2021, they had Lion 400 million, an open data set. And this is basically 400 examples of pairs of images and text. And it's very useful to train text-to-image models. And then next year, they released Lion 5 billion. So it's scaled significantly. And this scale is usually very important for diffusion models to work well and generalize. And then basically you can see more data sets for different reasons and different purposes. But these two are what commonly used to train diffusion models early on. And of course, companies, startups which have their own data set, for example, Google has access to lots of images, or some other companies may have different data set, internal data sets. Those are also typically used if the licensing is okay to train diffusion models. So this is a very good paper if you are interested to learn some of these details. It is published by Stability AI, This is the stable diffusion. It's slightly different from what we are going to explain in text-to-image because it's latent-based. We would talk about latent diffusion models in the text-to-video part of this lecture. But it's still a very good paper to read, and it explains the exact method of training diffusion models and data filtering, and all those things. So if you're interested, you can take a look and see what is the training data that they've used. I think it... Okay, but basically they are definitely going to talk about their training data, what they used and so on in their paper. I think I've... yeah, for the interest of time, I would skip this part, but there should be somewhere that they're discussing about their training data. So back to our lecture, this is all about data preparation. We will end up with very clean pairs of prompts and images after going through all of these, or we can start from some publicly available open source data sets like Lion 5 billion or 400 million. And then we can include this open source data and our internal data, if we have, as our final data to train our diffusion model on. So this is data preparation. The next part is model architecture. All right. Model architecture is basically what kind of layers to just put together and form our model. So we saw different neural network layers in week 1, and that's basically the idea. So over the years, people have tried different combinations, and they came up with some good architectures for different use cases. And for image generation, there are two very popular model architectures. One is UNet and one is diffusion transformer, or DIT. So initially, UNet was introduced, and it was introduced in this paper. And it was also introduced not for image generation, but it was for a biomedical use case. So convolutional networks for biomedical image segmentation, and it was published in 2015. But the architecture had some good characteristics, which makes it ideal for image generation. And this is the architecture. Basically, they have a bunch of convolution layers, and then downsampling layers and upsampling layers. So downsampling simply just downsamples, make the feature map or the input smaller. And then convolution layers, we saw, it's just a layer. It goes over, it goes through the image or the input, and it applies the convolution kernel. So if you're interested, you can search convolution on Wikipedia. There is really good definition of the mathematics behind it. But again, the architecture is like this. It starts from some input, which let's say it's an image, 2D image of some size. And then through a sequence of steps, it just makes this image smaller and smaller. And these steps are called downsampling layers. So it basically becomes smaller. It becomes 284 by 284. And then the depth or the feature length, it's getting higher. And that basically just a representation of those pixels. It's just the shapes. But the image is just getting smaller through a sequence of layers. And then at some point we have, let's say, these 32 by or 28 by 28 or 64 by 64. And then this is also downsampled to 32 by 32. And then basically now the idea is to have the inverse of these downsampling layers, or we can call them upsampling layers. Now it's exactly the opposite of these layers. It uses upsampling to make the images bigger and bigger. And also it interleaves those with convolution layers to apply the convolution operation and learn better and better features by capturing the locality in the pixels. But basically, after applying all of this, the output is going to be the exact, is going to have the exact shape as the input. And because of this, it's ideal because remember, in diffusion models, we want to start from noise or add noise to some image and try to denoise it. So the input is going to be an image and the output is going to be an image with the exact same size. So if you're interested, you can read the UNet paper. Again, it's mostly for biomedical image segmentation in this paper. But this is the high-level architecture. We have these downsampling blocks. I call them layers, but let's just call them blocks. And we have upsampling blocks. And if you look at each downsampling blocks, it's basically just a sequence of convolutions and maybe normalizations, activation layers, and so on. And similarly, we have upsampling layers. And upsampling layers, if we look at them, it's just transposed convolution. So it applies convolution, and then it just makes sure to increase the size of the input, followed by some normalization and nonlinearity activations. So, and this is how it's going to look like, the transformations. You start from this image, 64 by 64. At each step, it becomes smaller and deeper. And eventually, we are at 4 by 4 by 1024, very deep. So very good feature map per pixel, per 4 by 4 pixel. And then we apply inverse of it. We go to the upsampling layers until we get the final output here, which is the exact same shape. So this architecture turns out to work quite well. And these layers are going to learn good weights so that from an input image, it can predict noise or predict a denoised version of the image. So one more thing I want to note is that the original unit paper was not conditional, meaning that there is no way to include a text as part of the input or condition. So for these papers, there are different ways, and people have developed different solutions for it. But basically, the high-level idea is to encode the text using some text encoder. There are some text embedding models out there. We talked about text embedding models. They are pre-trained models that they accept the text, and then they convert it to some numerical vectors. And these numerical vectors are meaningful, meaning that if you look at the embedding space, text with similar meanings would be nearby. So the text encoder is used to go from text, like conditional text input, to some vector. And then that vector is used as part of the input. And then additional layers like cross-attention is used so that as the model is learning to come up with new features, it also attends to the text tokens. So somehow this layer makes sure to influence the this transformation process using the input text. So that's all about the unit architecture. And it was the first architecture that we used for training diffusion models. But then later, there was another paper called DIT, Scalable Diffusion Models with Transformers. It was published in 2023. And basically, the main innovation here was to switch from a convolution-based model to a fully transformer-based model. And that's where the T comes from. It's diffusion transformer. So let's briefly review diffusion transformer architecture. And then also, I want to point out that all recent models are based on DIT, not UNet anymore, because the presence of transformer and self-attention mechanism is very powerful and make the quality of images a lot better. And also, it scales with more data. So meaning that as we have more data and we train with more compute, we would get better models when we are based on, we are using transformer. So let's see what the architecture look like. All right, this is the DIT architecture at a very high level. Again, the purpose is just to keep some of these high level so we get an overview of all different models, all different techniques. But if you are interested, you can always go to the paper, Scalable Diffusion Models with Transformers. And you can read in detail how they've built it, why they believe this is a better architecture, and all the numbers and different experiments that they have tried. So feel free to take a look, but here is a simplified architecture. Basically, it starts from some input image, which is generally the noisy image. And then it goes through this sequence of layers. And this sequence of layers is, first it's patchify. So what patchify does, because it's transformer-based. So remember from week 1 that transformers expect a sequence of tokens. And image, noisy image, is not a sequence of tokens. It's just 2D pixels. So we need to go from these 2D pixel to a sequence of vectors. And this is the purpose of patchification or patchify. You can see this here from whatever input image we have, let's say 48 by 48. Patchify first, just logically divide this into some patches. For example, here we have 3 by 3 patches, and each patch, if you think of it, it's 16 by 16 because the original size is 48. Now, each 14 by 14 patch after the divide step is going to be flattened, meaning that there are 16 by 16 pixels, so we are just going to flat it into a long vector. So this vector is going to be 256. And then finally, here is projection layer, which we just use a linear layer to project this into a desired size. And that's important because we may want to have control over this dimension C for the transformer, because whatever we end up getting here, it's going to be what the transformer would receive as input. So it's going to influence the hyperparameters of the transformer. So that's the reason we have this projection layer, to go from this fixed number to something that we really want for the transformer to process. And then after the projection, we basically have now a sequence of embeddings, a sequence of patch embeddings. So each sequence is going to represent one patch or a certain region in this input image. And then after that, it's just the normal layers that we saw in like decoder-only transformer, LLMs, and so on. It's positional encoding to introduce positional information. And in 2D input, it's a little bit different. In 1D, it's simpler because when we have a sequence of words, basically we can just simply start from position 0, 1, 2, and so on. In 2D, we have two options. We can still have a 1D positional encoding. So we can name this position 1, 2, 3, and then here is 4, 5, 6, 7, 8, 9. These are the positions that we can assign. Or we can use 2D positions. So 2D is basically we have one dimension for row, one dimension for column. So this one is going to be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So this is positional encoding. I'm going to talk a little bit more about it when we go to the video training. But this is positional encoding, just to attach positional information to this sequence, like where each sequence is coming from, which part of which region of the input image. And then we have transformer, which is a sequence of transformer blocks. It just keeps transforming these patches. And then finally, the output of this transformer goes into the unpatchify. And unpatchify is the opposite of this. It converts this sequence into a predicted noise, or the final output. And all the conditions, including the text prompt, can be injected to the transformer. If we include, since we can include cross attention in the transformer. And cross attention is for a mechanism to update these embeddings by cross attending to external vectors or conditions. So this is overall the high-level overview of DIT architecture. So the next part that we are going to talk about is, diffusion training. And regardless of what architecture we end up using, whether it's unit or DIT, still they are, in terms of input output, they are similar. So the input is going to be an image or noisy image or random noise, and the output is going to be an image with the same shape, whether it's unit or DIT. Now, for training this model, using diffusion process, there are two steps: forward process and backward process. You should have some good idea about this forward process and backward process. We've already explained a little bit in the overview. But basically, during the forward process, we go from the clean image and we add noise to it up to a certain point. And this certain point, we call it T, meaning that T times we just keep adding some random noise to it. And then T is randomly sampled. It doesn't have to be a fixed number. Sometimes we can add less noise, sometimes we can add more noise. But this is basically the definition of forward process. We iteratively add noise to the input image from our training data to make it look noisy. And then we have the backward process. This is where the actual learning or training is happening. Now, this XT, which is the noisy image, it is passed to the diffusion model along with the conditions that we have, such as text. And this diffusion model tries to denoise it a little bit. Now, there are different formulations. Some papers have formulated it to output a denoised version of the image. Some formulation basically ensures that the diffusion model outputs a noise, like the noise that should be removed from this to make it a slightly denoisier. So regardless of that, it's just different formulations. A lot of papers suggested that for better training, it's better to have diffusion model to predict noise instead of predicting a denoised image. So regardless, the diffusion model predicts the noise in this image. We can reduce the noise and get a slightly less noisier image. So this is basically the backward process. We use the diffusion model to predict the noise in this image, and then the optimizer would update the parameters of diffusion model so that it can more accurately predict the noise given this image. So another thing is the loss function. And the loss function here is just very simple. It's in most diffusion models, it's a simple MSE, mean squared error. And what that means is basically whatever the ground truth is, the true noise that should be predicted, it's compared with the diffusion model's output, which is the predicted noise. And then we just measure the difference by looking at the pixels and calculating the difference and squaring it. So this is the forward and backward process and how we train this diffusion model using MSE loss to learn to predict the noise in a given noisy image. Now, to better understand, this is a training loop that we have here. So let me zoom in a little bit here. All right, so this is our training data set. And it has rows, millions of rows. And then we have one prepared image, which is nice, square, and normalized pixels. And also a good detailed caption. So this is our training data. Now, through the forward process, we randomly sample a time step in the step one. Step one is noise addition. We randomly sample a time step. And this time step is generally a value between 1 to 1,000. 1,000 means we add a lot of noise. 1 means we add just one step of noise. So the higher this T is, the more we are going to add noise to the image and make it less clear. So this is the noise addition process. Once we know the time step, we can apply the forward process. And forward process is simply adding a random noise to this image. And then we get the noised image at T equal 800. Let's say T is 800. Now, the step two is preparing the conditioning signals. One condition that we need to provide to this diffusion model during its denoising process is the caption, which we already discussed. A boat in an ocean is coming from the caption of this image. It goes to a text encoder, let's say clip, and then we get the sequence of vectors. Another condition that we must include is the time step, the randomly sampled time step. Because this is very important and it gives the diffusion model a signal that how noisy this image is. When these T values are very high, it means that this image is very noisy. And when it's low, it means that the image is less noisy. So the diffusion model can accordingly predict the noise based on the time step. These are the common external conditions that we need to prepare them in the step two. And then once they are prepared, meaning that they are represented in some numerical formats, they can be passed to the diffusion model along with the noisy image. And then we get into the third step, which is noise prediction. And remember, all we are discussing is just one iteration of training. So in each iteration, all these things is happening. So in this step, the diffusion process processes this image through a sequence of layers that we discussed. It patchifies the image, it passes to the transformer. The transformer just looks at all the neighboring tokens or embeddings. And then finally, it outputs something, and then we unpatchify it to get the final image. And then once we have this final image, since this model was expected to predict the noise, the correct noise, we can calculate the loss. And basically, the loss calculation is based on what noise we added initially here. So we have access to that. We can just compare it with the predicted noise and measure the difference. And once we have the difference, we can just, the optimizer now can update the parameters of this diffusion model so that next time with the same input, it can more accurately predict the noise. And this is one iteration of the training loop. If we just do it over all the training data, at some point, diffusion model would have parameters which are really good at predicting noise, given a noisy image and time step and caption. All right, this is all about diffusion training. Again, there are a lot of theories involved. If you are interested, there was this DDPM paper that we initially introduced. If you are interested to learn about the details of all the probabilistic view of diffusion models and why training should be formulated that way, why is it better for the diffusion model to predict the noise, not the denoised version of the image and so on, you can go through this if you're interested. It's math heavy. There are lots of theories involved. And so, yeah, in case you are interested to learn the details, you can just go over this. But the high level idea of the training is very similar to what we just explained. So that's training. Now, the next topic is sampling. And this is going to be short because after we train the diffusion model, it has very good optimal weights, meaning that for any given input image, if it's noisy, it is very good at predicting some noise, such that if you use that noise to reduce it from the input image, you would get a more clear, less noisy image. And once we have that, sampling is easy. So diffusion sampling is basically an iterative process. We start from a random noise. We randomly sample it using a sampler. And it's gonna look like this. And then we can also, since it's random noise, we can have a time step of 1000 or 999 because it's fully random. And then this is going to be passed to the diffusion model along with the input text prompt that the user provided, as well as the time step. At this step, the time step is 999. Now the diffusion model predicts the noise. And then from the noise, we can use it to reduce the predicted noise from this to get a less noisy image. And you can see now there are some visual cues, but it's still very, very noisy. But if we iteratively keep doing this, eventually we would reach to X1, which is a little bit noisy. And then we pass it to the final step to the diffusion model. And then we'll get X0, which is expected to have no noise and be very clear. So this is diffusion sampling. And traditionally, since during the training, we sample the time step from basically a number between 0 to 1000. For sampling, we traditionally start from random noise and then the time step in 1000. So what that means is that this iterative process takes 1000 steps. And that's why they are very slow and it takes a lot of time. But there were some other papers like DDIM paper, if you search it, which tries to formulate sampling in a different way and remove the stochasticity out of it. So that it applies some ideas to go from 1000 steps to less steps. In particular, that paper, I believe it's doing in 50 steps. But then again, there are lots of techniques. It's an active area of research. There are different techniques like distillation methods to go, or consistency models to go from, let's say, 50 steps to a model that can denoise in 20 steps or 10 steps. And there are some, and the extreme case is that to train a model that can denoise in 2 steps or 1 step. But again, in practice, what companies usually use, which provides a good trade-off, a good balance between quality and speed, is like between 20 to 50 steps. So that's about diffusion sampling. All right, that's how typical diffusion-based text-to-image models are built. We prepare data, we use public data sets, we use either UNet or DIT. DIT is more recent and more advanced advanced T2I models are based on DITs. Then we train through the forward and backward process, denoising, noising and denoising. And then finally, we have this diffusion sampling. And this is misspelled. So this is how we built diffusion-based text-to-image models. Now, the next topic is how are we going to evaluate them? What are the common metrics? So let's go to evaluation. So evaluating a text-to-image model, we can evaluate it from different aspects. One is the quality of the image. Like basically, we can look at the generated images and we measure how good the quality of those images are. The other common and important aspect to evaluate models is their image diversity. Basically, the idea is we don't want a model that cannot generate diverse images. For example, if all the cat images or dog images that it can generate has a certain style, certain color, it's outside, it's not desirable. So ideally, we want models that can generate subjects, concepts in a very diverse setups. So it's very important to measure how diverse the images are. And finally, the last aspect is image text alignment. At the end, we want the generated images to also align with the provided text prompt. Even if the quality and diversity is good, but it's not really matching what we provided as prompt, the model is not going to be useful. So these are the three main areas to evaluate T2I models. And each of these areas have their own metrics. So we are going to briefly cover some metrics, and there are some papers for all these metrics. If you're interested, you can go and read the details. So for image quality and diversity, one common metric is inception score. And then this diagram summarizes the process, but basically it has 5 steps. The first step is to use the model to just generate some images. We have some prompts, we pass to the trained model, we generate the images. Now, in order to measure the quality of these images and also the diversity, Inception score relies on a pre-trained model. For example, Inception V3 is a pre-trained model which is trained to predict probability of different classes for a given input. So it was a model that was trained for a very different purpose for a classification purpose. So there are a certain number of classes. The input was images, and then the output of this Inception V3 was class probabilities for different categories or classes. But the idea is if we use this pre-trained model to get the class probabilities, it would be a good indicator whether these images are fitting into one of those 1,000 categories or classes, for instance. So if, for instance, these probabilities are very flat or not sharp, it means that it's not very clear from the image what category it belongs to, and that is not ideal. So we use Inception to get these probability distributions, and ideally, each of these probabilities should look not flat. They should look sharp. So the second step we already went, it's computing class probabilities. The third step is calculating the marginal distribution. So marginal distribution, we can think of it as kind of like an average of all these probabilities. So let's say we get something like this. And this marginal distribution is important because of 2 reasons. One is that it is a good indicator for diversity. If these images are diverse, if you take, let's say, average of these probabilities, we should get something flat now, because ideally we want to have images in all different categories of Inception V3. The other advantage of this marginal distribution is that now it can be compared with these individual class probabilities, and we can measure the score. Basically, what we want is that if we want these probabilities to be sharp, not flat, we want them to be, basically, we can use a KL divergence. It's a measure to, it's it basically measures how different this probability and these probabilities are. And we want these numbers to be high because ideally we want each of these probabilities to be sharp, not flat. And this should be flat. So again, I'm just trying to be very intuitive and high level. If you are interested to learn the exact mathematics, you can read the papers. But this is the fourth step, which we get a score per image. And then finally, these scores are just combined and we calculate the inception score through averaging or some other more complex aggregations. So this is how inception score is calculated, and it's a measure of both quality and diversity of a model. Another very important metric which is used is FID for measuring quality and diversity of images. And it's following a similar setup. It's still relying on Inception v3. It's slightly different. So we start from this model, we generate images, and these are fake images. The main difference is that now we compare them with real images. And the idea of FID is to look at the difference in the representation of real images versus fake images if we use a pre-trained model. So to better understand, we have these fake images and real images. We pass it to Inception v3 and we get class probabilities, let's say vectors of size, depending on number of classes, let's say 1,000. And we do the same for real images. Now, from these these vectors for real image, from real images, we can just calculate a mean and covariance. So these two vectors are going to represent the statistics of all these features coming from real images. And we do the exact same thing for fake images. So we compute the mean and covariance between all these pairs of features. So these two numbers, these two matrices, basically represent the statistics of fake images. And then we apply some distance measure between these two. I'm not going to go into the details, but if you are interested, you can read the FID paper. But basically, it's just a very particular measure to calculate the distance between these statistics of real images and statistics of fake images. And this final number is going to show us how high quality and diverse, and basically it would give us a number that tells us how real the fake images look like, how similar their statistics are compared to the real images. So these two metrics are traditionally used to measure the quality and diversity of images. Now, this is for image quality and diversity, but one last thing was image text alignment. How do we measure that? A common metric for that is clip similarity score. We already talked about clip model. We saw that there are two encoders, text encoder, image encoder, and it's trained on it's trained to learn a shared embedding space, meaning that if an image and a text has semantically similar meaning, they would be nearby in this embedding space. Now, this is going to be very useful to measure the alignment, because now for each text, when we pass it to our text-to-image model and we get an image, we can use this clip model to map them into this embedding space and then measure their distance. If the distance is close or if the distance is small, it means that there is a high alignment between the text and image. And if they are far, it means that the generated image is not really aligning with the provided text. So these three metrics are generally used to evaluate text-to-image models. So that's basically everything about text-to-image models, how we train them and how we sample them, how we evaluate them. Next, we are going to switch our focus to text-to-video generation. Hey, let's switch to text-to-video and we understand what's the landscape there and how can we build text-to-video models and extend a text-to-image model to work with video data and generate video data. After the success of diffusion models in generating images, very soon this work came out, and there was also a paper named video diffusion models, and they try to extend the unit model to work with video data. And then these are some of their examples. Again, back then it was impressive. In today's standards, it looks a little bit too simple and not very impressive. So this is very early work right after diffusion models were becoming popular. And I believe this was a work by Google. And then right after this, in a very similar trend to images, also companies, researchers started building and improving text-to-video models. And then there were some companies also introducing their own family of text-to-video models. For example, Google introduced Veo, and then Veo 1, Veo 2, and more recently Veo 3. Also, OpenAI introduced Sora, their text-to-video model. And there are a bunch of other companies that are that have introduced their own text-to-video model and are keep improving them. For example, Kling, Van, Cdance from ByteDance, and so on. This is when Sora was published in February 24, and basically it says video generation models as word simulators. They are not really discussing the details or architectural details. All they are sharing is that it's diffusion based, and they are using a compressor to compress the pixels into a smaller latent space. And that's it. That's all we know about Sora. There is not much more that we know. There is another paper called Open Sora. Basically, the community, they came together to build something similar to Sora, and they use various advanced techniques to make it as close as possible to Sora. But basically, that's all about OpenAI Sora. And then Veo is here, and you can see these videos are generated. So if you compare it with the original video diffusion model videos, you can see the huge progress there. And I would say Veo 3 is also doing a quite impressive job. Also, their model is capable of generating audio along with the video, which is also impressive. And again, these are all AI-generated content, which seems it's super impressive. And it's also accessible here in the ChatGPT UI. If you click on Sora, you can see, you can explore all the generated content. You can also generate your own content. All you need to do is to describe your videos. This is where the prompt goes. And then they give options to choose the type, let's say video. We can specify the aspect ratio that we want, whether we want portrait or square or landscape and different ratios. Here we can also specify the resolution, and they support up to 1K resolution. Here is the duration of the generated video. They support from 5-second to 20-second long videos. And then here it says T2V, and you can choose 1 video, 2 video, 4 videos. All right. And then a bunch of other options. So basically you enter your prompt here and you get a video. Just to get a sense, again, these models are not there quite yet. They are very impressive, but there are, if you enter certain prompts in certain domains, which the data set was not really too comprehensive in that domain, the model may not do a really good job. For example, I used the same prompt that we used for generation, the taco example. And I asked a taco studying machine learning at sunrise on a mountain. And both videos are looking a little bit silly to me. And I specified high resolution 10 seconds. So in both cases, the taco disappears suddenly. And this one, the laptop just turns and suddenly the taco appears again. Again, these are not good videos. Just I wanted to get a sense of how Sora would work on a similar prompt like that. So, and again, we have a leaderboard for video models. Right now, the recently introduced Cdance by ByteDance is ranked first. And then right after that, we have VO3 by Google, and then VO3 Fast, and basically more models like Kling. VO2 VO2 is here, and then Sora right now it's 10, so it's not really one of the most advanced ones anymore. And all these models are not open. So the best video models out there are not open. The first one that is open is this one from Alibaba, Van. And also they are doing good, quite good. This model is quite recent and it made it to the top 10, so it's amazing. But except this, all other models are not open. So, but let's see, how can we build text to video models? How is it different from text to image models? So text to video is very similar to text to image in many cases. In a text to video system, basically the goal is the input is a prompt and the output is a video. And video is basically a sequence of frames. For example, it can be 120 frames. If you just put them together, it would form the video. So in a text-to-image model, the output is one image. In a text-to-video model, in this case, the output is 120 frames. So it's very similar to text-to-image. The only difference is that it's a lot more expensive because now the same model has to generate not one image, but hundreds of images, or we call them frames. Let me close these Sora ones. They are very heavy. It's going to be very expensive compared to text-to-image models. So there are a lot of challenges and optimizations required to make it work. But at the end of the day, it's still an image generation problem or a sequence of images generation problem. So a lot of the architectural details and training details still is exactly the same as diffusion models. The main idea that is different in video text-to-video model is the idea of latent diffusion models. And basically, the idea is to, instead of operating in the pixel level, pixel space, we operate in a lower dimensional space, and we call that latent space. And this makes things more efficient. So instead of having this model to generate 120 frames in the pixel space, if we just compress everything into a lower dimensional space and then ask this T2V model to also generate this video, but in a lower dimensional space, it's going to be more manageable in terms of cost. And this is what latent diffusion models are. We use a compression model or compression network to go from the pixel space, from the original video, to some latent representations. This step is very important because original, like videos, they have a lot of duplications, and a lot of neighboring pixels a lot of times are similar. And if you look at two neighbor frames, they are also very similar. So if we have a compression network that can go from this dimension to a lot smaller dimension, both spatially and temporally, it's going to be more manageable because now our diffusion model needs to be trained on these representations to denoise. And so all we need basically just a network that can go from pixel space to latent space, and also it can go from the latent space back to the pixel space. So let's see how much it's going to impact the performance. So before that, again, the compression network is also a neural network, and it has two parts, an encoder and decoder. The encoder is responsible for mapping the original video into the latent representation, going from pixel space to latent space. And then the decoder is exactly opposite of that. It goes from this latent representation to the pixel space. And this setup may sound familiar to you, and that's VAE, which we saw earlier. So remember, earlier I mentioned that VAE is no longer used for image or video generation, but it still has a very important use case, and this is its use case. VAE or some variations of VAE are used as compressors, as a compression networks. They compress the input into a lower dimensional space so that we can train our diffusion model only in this lower dimensional space. So things going to be a lot more efficient. And just to get an idea of the impact, let's say we want to deal with videos of size 1280 and 720 and also 120 frames. If you multiply these numbers and count all the pixels, it means that this the videos that we are dealing with has 110 million and something pixels. Now, if we use a compression network to compress this, we may end up with something like this. For example, if we compress the temporal dimension, 120 frames, if we compress it by a factor of 8, we would get 15 frames only. And similarly, here and here, if we use a scaling factor of, I think, 8 here, and perhaps 8 here as well, we would get 160 by 90. So all we need to do is we need to train a VAE model with a downsampling factor of 8, both spatially and temporally. And by doing that and encoding the input video, we go from 110 million pixels to only 216,000 pixels. So it's around 512 times more efficient. And that's why compression networks are very important. Even in the Sora blog, they are talking about this compression network and how they are encoding and going from the pixel video into a latent space in lower dimension. So that's compression networks. Now, all we need to do is we need to train a diffusion model in this latent space. And that's what we are going to talk about next. But very similar to image generation, it has 4 parts. It has data preparation, then we need to figure out the model architecture, model training, and sampling. But it would overlap a lot with text-to-image model, so it's probably going to be shorter. So let's start with data preparation. Very similar to text-to-image. Now it's text-to-video. So our data is pairs of captions and videos. And preparation is basically we need to filter bad videos, and we also need to make sure that our captions look nice. So again, everything is very similar to the text-to-image model. For filtering, common things that we have to do on the videos is we filter inappropriate videos. We can use pre-trained models to identify videos with licensing issues, logos with violent content, nudity, and so on, and we just remove them. We can also use some other models or some heuristics to remove low quality or short videos, to remove duplicated videos that are near duplicate or very similar, and also removing harmful videos. So these are common filtering techniques that we need to apply to our original training videos. And then we get something like this after we're removing bad videos. Now, the next thing is we need to standardize these things, because many of these videos may come in different durations, different resolutions, and even different formats. So it's very important to make sure that we have convert all of them to a standardized format. And that's the purpose of standardization. So we adjust the video length. So for example, for longer videos, we can just sample 5 seconds or 10 seconds of it, like smaller duration. We can standardize frame rate. We make sure that all the videos are having a fixed frame per second or FPS. And if not, we can re-encode them. We also need to adjust the video dimensions spatially. So that can be done by resizing and cropping, similar to images. And after all those standardizations, we get something like this. Now, the next thing we need to do is, again, we are not going to operate in the pixel space. We are going to operate in the latent space. So now this step is using a VAE that, let's say, we can train on videos, and we pre-compute the latents. Basically, once we have the VAE fully trained, we can use it to convert all these videos into their latent representation. And we can pre-compute that during the data preparation process before training our main diffusion model. And once we have these very small latents, we can just store them in some storage for training. And captions are going to be the same as images, so we are not going to cover them. Basically, we can make sure that captions are accurate and detailed. If not, we can use some vision language models to recaption videos and make sure we have very clean, detailed, accurate captions. And then once we have the captions, we can tokenize them or pass it to some text encoder to get a sequence of vectors. And eventually, this is going to be our training data, a bunch of video latents and caption embeddings for conditioning. So this is our data preparation. Next is model architecture. For the model architecture, again, some very earlier works started with UNet and extended it to work with videos by injecting some video-related layers. But since DIT is the major model that are being used these days and the standard model, we are going to focus on DIT. So for text-to-video model, we can still use DIT, but we need to extend it to work with video inputs. Remember, this was the DIT model. Some images goes in. We have Patchify to convert this noisy image into a sequence of vectors. Then we inject positional information into those vectors. And then that sequence of vectors is passed to the transformer, and it gets transformed through a sequence of blocks. And finally, the output of transformer, which is a sequence of vectors, goes to unpatchify, and they are we unpatchify them so that the final output has the same size as the input image. Now, in order to extend this architecture to work with videos, we need to think about what needs to be changed, because now the input is going to be a video, and a video is just a sequence of images. So now it's a 3D. It has a temporal dimension as well. So first thing that needs to support 3D inputs is Patchify, and it's very simple to add support for 3D inputs to Patchify. For images, Patchify was like this. The first step is dividing the image into patches, and then each patch is flattened. And finally, these vectors are projected into a different dimension. In videos, it's still going to be very similar. The divide logic can divide it not only across the spatial dimensions, but also across the temporal dimension. So it's a cube now, and each patch is also a cube. And this cube now, we can still flatten it because it's just a sequence of pixels. It's just 3D pixels. So if we flatten it, it's going to be just 1D vector. And from this point forward, it's going to be the same as images. We have this sequence of vectors, and then we can apply projection to bring them into the desired embedding size. So here, for instance, we have 9 different tokens, or the sequence length is 9, and that's because the image has 9 patches. Here in videos, it has 1, 2, 3 times 3 times 2, 18. So the only difference is that with video data, after Patchify, the sequence length is going to be more, depending on the temporal dimension. So that's one modification in the Patchify layer to support 3D inputs or video inputs. The other one is positional encoding, which we need to add support. For images, positional encoding, we can just assign positions to each patch, like 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we can have some functions to go from these numbers, these positions, to some vectors. And there can be some fixed functions, some learned functions. So we'll talk about that in a bit. But that's positional encoding in 2D. Now in 3D, the main difference is that how are we going to number this? We can now number each cube like 1, 2, 3, 4, 5, 6, and then temporally we can go one by one. And then once we have these 18 positions, we can just pass them to the positional encoding and get these 18 positional encoding vectors. So that's the main modification we need to add to the positional encoding. Basically, now we need a positional encoding that handles these 18 kind of positions. And this is if we decide to do 1D kind of positional encoding. There are different ways that we can design our positional encoding. So what we saw was 1D, meaning that we have a function that can convert any number into a vector. But we also mentioned that for images, we can have a 2D kind of design for positions. So 1, 1, 1, 2, 1, 3. And then the main difference is that now we need a function that can map 2 dimensions into a vector. Everything else is the same. We just need to design the right function to go from 1D or 2D positions to a vector. And for videos, it's also the same. We can have this 1, 2, 3, like 1D encoding of a video, and we use a function to map to a vector. We can also have 3D encoding of videos. So each cube is going to have 3 numbers, a spatial column, spatial row, and temporal dimension. So for example, here it's 111, 112, 113, and so on. So the design of positional encoding function, it's up to us. There are different functions we can use. But regardless of which function we use, if we are dealing with 3D data, and if we decide to do 3D encoding, we can come up with something like this. If we are going to keep everything 1D, we can keep something like this. So that's the change in the positional encoding layer. And then Unpatchify also needs to be changed, because now the Unpatchify has to output a video, like a 3D output. And it's going to be very similar to what we saw in the Patchify. Now on Patchify, it gets a sequence of vectors, and we send it here. And the reshape is basically the main part that needs to be modified, so that after the reshape, it ensures that the final output or predicted noise, it has the same shape as the 3D input. So after making these adaptations into these layers, the same DIT now can support 3D, both 2D and 3D inputs. And then the conditions and everything else remains the same. We can just prepare the conditions, pass them to the transformer, and transformer has this cross-attention layer, which cross-attends to those conditioning signals and influence the updates or the final generations. So that's all about model architecture. Now let's go to model training. Training is also very similar to the image diffusion models. It has the same loop. And then for each training pair, we just add noise to the video. Then we train the diffusion model to predict the noise. And then we calculate the loss, like MSE, and the optimizer updates the parameters of the DIT model. But as we saw in video data, we have this temporal dimension. So these sequences can be very long, especially if we are in a pixel space. So there are more challenges. For example, in video training, text-to-video training, we have lack of larger scale video text data. In the image space, we have lots of image text data. We saw some public data sets having 5 billion pairs of image text. We don't have something similar for video data. So that's one challenge. And the other challenge is obviously the computational cost of video generation, and especially high resolution video generation. So let's talk about some of the mitigations for these challenges. For the lack of larger scale video training data, what papers or companies commonly do, they train on both images and videos. So we have these image text pairs and video text pairs. And basically, we take advantage of both of these to train a model. Now, there are two strategies. One is we combine both of them, and then we train a video model on both of these. Because again, the reason that we can do this is because images can be considered videos, just having one frame. So anything that works with video data, it can also work with images. So one strategy to use both data is to just put them together and train a single model on all of them. Another strategy, which is also common in many papers, is to first pre-train on image text pairs and train an image model. And then we continue training this image model or fine-tuning it on video text pairs to get the video model. This setup might be faster to converge because first we have a model that learns all the spatial information, concepts, colors, objects, and so on. And then using the video text data, it would learn the temporal aspects of things like movements, actions, and all those things. But regardless of which strategy we use, it's common to use and take advantage of images as well when we are training video models. For efficiency, for computational and efficiency challenges, there are different techniques that are often used in practice. One is an LDM-based approach, which we already discussed. We train a compression network or a VAE to convert pixel space to latent space, and we train our diffusion model in this latent space only. We also can pre-compute these representations during the data preparation. Basically, we don't want to compute these latents during the training time of training the actual diffusion model. So it's common to pre-compute these things. And the other thing is that a lot of times we want the final output video to be high resolution and also have a certain duration, like 10 seconds. However, if we train our diffusion model to output very high quality or long videos, it's going to become very expensive. So in practice, it's common to train separate models only for those tasks. So we can train a spatial super resolution model which is only responsible to increase the spatial resolution of some inputs, and also a temporal super resolution, which is responsible to increase the number of frames or increase the temporal dimension of a given video. And there are also some other techniques like using distributed training and so on. But then the final workflow would look something like this. We have this latent diffusion model, which is capable of generating videos, but in the latent space. So it's very small, and this is not directly usable. If we visualize it, it's not probably looking like a video because it's not in pixel space. Now, after the latent diffusion model outputs this latent space, we can use the decoder part of the VAE or our compression network to bring it into a pixel space. Now, this is going to be a video, and if we play it, it looks nice. But now the problem is it's especially not high resolution and also only 60 frames. Now, these can be passed to this spatial super resolution, which has 4x upsampling. So what that means is that spatially, it would 4x the resolution while keeping the number of frames unchanged. And then temporal super resolution, 2x upsampling, would keep the spatial resolution unchanged and would increase the temporal frames. So what that means is that, for instance, originally we can have a model that generates videos with 12 frames per second. And then temporal super resolution can just increase it to 24 FPS, which is, let's say, the default, the desired video FPS. So this is a typical pipeline that we can use to manage the efficiency side of things. And that's all about training challenges. The training itself is exactly similar to text-to-image training. Now, after training, the next topic is sampling or generation. This is also, we don't need to change much. It's very similar to text-to-image. We need to start from some random noise. Now, the difference is that this random noise is going to be 3D, and also it's going to be in the latent space because that's the space that the diffusion model is trained on. So we randomly sample a latent noise. We pass it to this latent diffusion model. We have our text prompt. We pass it to the text encoder to prepare the conditions, and it's passed to the latent diffusion model. And then latent diffusion model, through a sequence of steps, iteratively denoise this random noise. And finally, it outputs the denoise latents. And in order to visualize that, we use the visual decoder part of the VAE to go from these denoise latents to generated video. So this is the generation process of videos. And again, if we want to use super resolution, both spatial or temporal models, we can just cascade it and pass this to those models to get higher resolution video. So that's generation. Let's briefly look at the final system design of a model like Sora or even text-to-image models. What we trained, the diffusion model or latent diffusion model, is this. So it's still a small component within the entire design of such systems. So let's just briefly go over all the steps that happens when a user enters a prompt. So the first step, as soon as the user enters a prompt, is prompt autocomplete, or there could be also It can be heuristics or it can be machine learning based, but basically it's a component that suggests you how to complete or possible completions of your prompt. And you've seen this in multiple places. In Google, when we search, we see autocompletes and so on. So this part is not a big deal. It's just there for more like convenience. And then when the user submit some prompt, first the prompt goes into some guardrails, or here we are calling it safety service. There are different terminologies. But basically this service is responsible to process the prompt and figure out if it's a safe prompt or not. If the prompt, for example, is asking for certain inappropriate videos, this component would identify, and if it's not safe, it would reject the request. And if it's safe, now it would send it to the prompt enhancer. Prompt enhancer is responsible for improving the provided prompt. Because a lot of times in the original prompt that the user submits, there might be some issues. It might be vague. There might be some spelling issues, grammar issues, and it might not be as detailed. So this component is responsible for figuring that out if needed, paraphrasing it, and also adding more details. After this component is done, we have a really nice, accurate, detailed prompt. And now this goes to this video generation component. Video generation is just interacting with the LDM, the trained model, and text encoders to sample from the LDM model. And then the output of this is basically the predicted output, but in the latent space. Now that goes into the visual decoder of the VAE to go to to convert the latent space output to the pixel space. Now at this point, we have a harm detector or output guardrails. And that's important because sometimes the models may produce something that is inappropriate. So this component is just responsible to make sure that if the predicted or generated video is not safe, we still reject request. And if it's safe, then we can pass the video to spatial super resolution to increase the spatial resolution of the video. And then we pass it to the temporal super resolution to increase the temporal resolution or increase the frame rate per second of the video. And the output of this is going to be the final video. All right, that's all about text to image generation, text to video generation, different components, how they are built, how they are trained, and we can sample, and also overall system design of building those systems. Later in the project, we would see how can we load some models and generate some actual content like images or videos. And also we would see how can we build a ChatGPT-like mechanism where you can use the same AI into your prompt. If your prompt is just a generic question, it would answer. If it's a request for image generation, it would generate an image. And if it's a request for video generation, it would identify that and pass it to the video generation model. So that's all about text to image or text to video generation models.